System properties in terms of impulse response. So here we are dealing with LTI systems. Already our system is linear and it is time invariant. So we are going to check the other properties of the system, that means causality, stability, memoryless and invertibility. So in terms of impulse response, as we already know, the input and output, that means the relationship between input and output of an LTI system is completely characterized by impulse response. Hence it is worth to examine the other properties of the LTI system in terms of impulse response. So let us check the first property, that means causality of LTI system. Causality of LTI system. So as we already know, the system is said to be causal if it depends on present and past values of the input. That means the output of the system depends on present and past values of the input, then we are calling it as a causal system. If the system output depends on the future values of the input, then we are calling it as a non-causal system. So this is the general definition for a system to be causal. So now we are particularly dealing with the LTI system. So let us consider a discrete LTI system, so whose output that has been given by y of n equal to x of n star h of n. Here x of n is the input, h of n is the impulse response and y of n is the output. So as we already know, the convolution sum which obeys the commutative property, so I can write this as y of n equal to h of n star x of n. So now I am going to write the formula, summation of k equal to minus infinity to infinity, so h of k into x of n minus k. So let us split this summation, that means y of n equal to summation of k equal to minus infinity to minus 1, that is h of k to x of n minus k, the plus the one more I am going to write k equal to 0 to infinity, then h of k into x of n minus k. Now look at here. So now I am taking particular case at n equal to n naught, say at some value. So it becomes, above equation become y of n naught equal to summation of k equal to minus infinity to minus 1 h of k x of n naught minus k plus summation of k equal to 0 to infinity h of k x of n naught minus k. Now let us expand this one. So if I expand, I am getting y of n naught equal to, say initially I am going to put the k value as minus 1. If I put k value as minus 1, then I am getting h of minus 1 x of n naught minus of minus 1, then it becomes plus 1. Similarly for h of minus 2, I am getting x of n naught plus 2 plus so on. So on up to minus infinity. So that is the expansion. Similarly do the second expansion. So plus, so I am going to do the expansion of this one. So k value starts with 0. So it is h of 0. So x of n naught only. So because k value is 0. Similarly expand h of 1 into x of n naught minus 1 plus h of 2 into x of n naught minus 2 plus so on up to plus infinity. So this is the expansion. So now let us look these equation. So carefully observe this one. Here I can tell that, so this x of n naught is the present input. In this, it is the present input. Here x of n naught minus 1, x of n naught minus 2. So these are all past inputs. Then x of n naught plus 1, these are existing here. X of n naught plus 2, so on. These are future values of the input x of n. So that means, look at here, the system has to be causal, means it must and should depend on present and past values of the input. The system output must depend on the present and past values of the input. The present and past values of the inputs are present in this bracket. That means this summation will give this expansion, this summation expression. So this is giving the causality condition. So now what about this one? H of minus 1 into x of n naught plus 1, h of minus 2 into x of n naught plus 2. So here x of n naught plus 2, x of n naught plus 1, all these are future values. Though it should not depend on these values, That means this entire summation, that is k equal to minus into minus 1, h of k into x of n naught minus k, I need its value as a 0. Then only I can say that my system output, this y of n naught is my system output, that is depending on present and past values. So now this has to be 0, means look at here, this x of n naught plus 1, x of n naught plus 2, all these are inputs, input signal, and it need not to be 0. Hence the left out condition is this h of minus 1, which is equal to h of minus 2, which is equal to h of minus 3, which is equal to so on, which is equal to 0. So this has to be 0. So then only this product will become 0, because your x of n naught plus 1 has to be multiplied with something. Then you should get the 0 value, means this value must be 0. H of minus 1, h of minus 2, h of minus 3, so on, which is equal to 0. So this is the condition for a causality in terms of impulse response, because h of n will give you, h of n is the impulse response. So hence I can write mathematically it as a h of n equal to 0 for n less than 0. Look at here, n less than 0 means n value is minus 1, minus 2, minus 3, minus 4 till so on up to minus infinity. For that value, if my h of n equal to 0, then I can call it as a system is causal. Similarly, for the continuous time signal, I can write here h of t equal to 0 for t less than 0. So this is for discrete time, this is for continuous time. So this is the condition for causality. So if I want to tell, or if I want to define causality of a system by using this impulse response, then this is the condition. So h of n must be equal to 0 for n less than equal to 0. So if the system satisfies this condition, then I can say that the system is causal, otherwise the system is non-causal. So similarly, we go for the next property. So that is nothing but stability of an LTI system. Stability of LTI system. Stability of LTI system. So already you know the system is said to be stable if it has a bounded output for every bounded input. So then we are calling it as the system is stable. That is a general definition of a system. So now particularly we are looking for LTI system. and we are defining stability in terms of impulse response. So that means for an LTI system, that system has to be stable if its impulse response is absolutely summable for a discrete time LTI system. That means if it obeys the condition summation of k equal to minus infinity to infinity, so h of k, its value must be less than infinity. That means if it is absolutely summable, then I am calling it as a system is stable. So this is for discrete time. Similarly for continuous time, I can write integration of, so tau equal to minus infinity to infinity h of tau with respect to d tau. If its value is a finite, then I am calling it as the system is stable. So that means in simple words we can tell that, so after this evaluation, if we get a finite answer, so if the answer is other than infinity, so then I am calling the system is stable.